So, we continue our discussion on central forces. One very important aspect of central force which we have already discussed briefly is that, so far we have considered the force center to be stationary. So, let us say we have assumed that this is the center of force and at any point in space the force F is proportional to the distance from this force center and it is towards or away from this particular force. Now, typically what happens if we consider the interaction between two gravitational interaction between two bodies or electrostatic interaction between two charged particles, then typically what happens? We have a bigger body, for example, the sun, and we have a smaller body which is, let us say, could be any of the planet, let us consider it to be Earth. And the smaller body is evolving. So, the gravitational force of attraction is taking place, acting along the line joining the center of masses, and it is an attractive interaction in nature. Now, for this interaction, Earth is evolving around in an elliptical path around Sun. Now, in this entire process, Earth is experiencing the gravitational pull of the Sun, but at the same time there is a gravitational pull of Earth that is being inserted on Sun. And so far we have neglected that because we have assumed that force center is stationary, that means Sun is not moving under the attraction of Earth, but Earth is moving under the attraction of Sun. Now, we have to systematically check whether this is a valid assumption or not, because typically what happens, although very small, this force of attraction which Sun experienced due to the presence of Earth or any other planet, combining all the planet, this interaction is also not very small, and there is a good chance that the Sun position is also shifting just because of these interactions. And also, as we all know, we all might know that Sun is just a simple star in this galaxy. Okay? So, galaxy is also not very special. There are many other galaxies in this universe, and inside the galaxy there are millions and millions of stars. Sun is just one of them, and it is placed not at the center of the Earth, the center of the galaxy, which was a belief at some point of time, but it is also placed slightly off center. So, due to there are many other heavier masses, and also Sun mass is a very moderate mass compared to other stars. So, there are many other masses around this solar system which are attracting this not only Sun, but Sun and Earth alike towards them. So, the whole solar system, although the Sun to Earth force, for example, this distance is not probably changing with time, not the orbit is not probably changing with time, which is not true again, it is changing slightly, but most importantly the entire solar system is being pulled in different directions. So, the solar system as a whole is moving, the galaxy as a whole is moving. So, there is a huge many types of gravitational interaction taking place. So, if we try to model this and see if the effect of Earth is indeed significant of Sun or not, what we need to do is, we need to just consider this two body system. Let us assume that there are 2 point masses M1 and M2, and let us assume that M1 and M2, they are the position vector is measured with respect to some origin O, okay, and position vector of this one is R1, position vector of this one is R2, and let us assume this to be some small r. So, we can immediately see R2 plus R is equal to R1, which we can rearrange to write R. So, these are vectors, sorry, excuse me if I mix the color a bit, but I think it's okay. So, R is equal to R1 minus R2. So, we have 2 point masses, and let us assume that overall external force which is being experienced by this 2 mass system. At the position of M1, this magnitude of the force is F1 external, and here the force is F2 external, right. So, if we try to write the force equations, and of course, there are internal attractive forces or internal forces, we can just call it. Force on M1 due to M2, we call it M12, which is acting along this direction. Force on M2 due to M1 is F21, which is acting along this direction. So, F12 is, okay, let us forget about this arrow. F12 is acting in this particular direction. F21 is acting in that particular direction, but from Newton's third law of dynamics, we can immediately tell that F12 is equal to minus F21. Okay. So, these are vector equations. Of course, the magnitude of these two forces are essentially equal. Right. Now, if we try to write the equations of motion for these two mass points M1 and M2, what we get is M1 R1 double dot. Okay, I hope this is visible to you, equal to F12 plus F1 external. Please understand this F1 external and F2 external, these are two vector quantities. Similarly, at site M2, we can write M2 R2 double dot is equal to F21 plus F2 external. Now, if this happens, now what we can do is we can multiply this with M2. So, we have M2 here and M2 here. We can multiply this with M1. So, we have M1 here and M1 here. Now, if we add, or rather we subtract this 2, we have M1 M2 R1 double dot minus R2 double dot, okay, which is equal to, now you see, if we subtract, it will be M2 F12 minus M1 F21. By using this relation, we can write the entire thing in terms of F12, and it will be M2 plus M1 F12. Now, for the last term, once again what we can do is we can take out, or rather I will just write it just below this, so that easy for you to see. So, once again we can just take out M1 M2 common from the last two terms, that means these two terms. So, the first term will be F1 external by M1 minus, and the second term will be F2 external by M2. Is it visible? Yeah, it is visible. So, we have, so the equation altogether can be written as, now what we are going to do is, in the left hand side we are just going to use R to be equal to R1 minus R2. So, left hand side we have, okay, and then yeah, so we can just rearrange it, R double dot, which will be equal to M1 plus, okay, I will not write it again. What I will do is I will simply replace left hand side by M1 M2 R double dot. Okay, so this is our equation of interest. Right. Now, look at this third term here, which is F1 by M1 divided by minus F2 by M2. Now, F1 by m1 is what? F1 is the net external force that is being acted on mass m1, and F2 is the net external force which is being acted on m2. Now, consider this situation. Let us say we have this sun and earth system, which is somewhere in the galaxy. All the big stars and all the rest of the galaxies exerting some force on this system. Now, due to this force, assuming that the net effect of all this force combined on this two body system is that both the masses are accelerated equally, then F1 external by m1 is the acceleration. Please understand this. F1 external by m1 is the acceleration of mass m1 due to this external force. Similarly, F2 external by m2 is the acceleration due to mass or acceleration of mass m2 due to this external force. If the overall effect of all these forces is not affecting the internal interaction, but it is shifting the two body system, or it is producing equal acceleration in the two body system, then this term essentially cancels out. So, what we are doing is we are taking the entire effect of rest of the universe as this including these into the external forces, and we are saying that this the acceleration of these two masses are equal due to effect of this external forces. So, if that is the case, then this term essentially goes to 0, because the accelerations of these two masses are equal due to the combined effect of combined external force, which leaves us with this two terms only, and we can rearrange the equation to write r double dot is equal to, or rather we can write this as mu r double dot to be equal to F12, or we can just write this as F, assuming that this is the magnitude of internal forces. I am just equating this equal to F. Okay. So, this is the equation with mu equal to m1 m2 by m1 plus m2, and this is called the effective mass. So, we see, assuming that all the external forces combined is producing an equal acceleration in these 2 point masses, the equation of motion is strictly a function of both the masses with this effective mass or reduced mass, or you can also call it the reduced mass if you like, okay, which is given as m1 m2 divided by m1 plus m2. Okay. So, strictly speaking, this is the this is how we should write equations when we are writing the gravitational equation of motion due to gravitational interaction between two masses. This is the equation we need to employ. We need to convert everything in terms of reduced mass, and I can tell you that the reduced mass will be essentially the center of mass of this system, okay, will be placed at a radius vector r, which is given by, okay, I will just write it here maybe, yeah. So, r will be the center of mass, location of the center of mass where this reduced mass will be located, which will be given by m1 r1 plus m2 r2 divided by m1 plus m2. Okay, so we will discuss this in details later on. That is not really essential at this moment. But now, what is important? Now, let us consider the situation. Let us consider Earth and Sun system. We know that solar mass is many times greater than the mass of this planet. Now, in this particular case, we can consider m2, or let us say m2 is way greater than m1. If that happens, look at this expression of the reduced mass. What happens is, if we put m2 lot greater than m1, then the denominator is essentially m2, because m1 has hardly any effect on it, and we get mu. In this particular case, mu is almost equal m2 m1. Okay. Now, if this happens, right, and then if we look back into this expression, then what happens in this under this particular assumption is that m2 is lot greater than m1. This one essentially becomes m2 r2 by m2, which is equal to r2. So, when see the first term will be neglected. So, what we see is when one mass is very dominant over the other, then the in equation of motion we can essentially replace the reduced mass with the smaller mass, and the center of mass essentially shifts on the bigger mass r2, right. So, that is what we see here, and this is why, especially when we are discussing gravitation, we can consider the bigger mass. Most of the time when we are discussing solar system, the bigger mass is the sun. So, because solar mass is lot greater than any of the planet masses, you can find the numbers from internet, exact numbers. So, that is why it is always safe to assume that effective potential. So, and the equations we are writing essentially will reduce to the mass of the planet times r double dot is equal to f, f being the gravitational attraction. But please remember this particular form, and so when we are dealing with two systems or 2 point masses or point charges, for example, which has almost equal mass and they are attracting each other, and if we want to write the equation of motion of that particular system, we have to employ the concept of reduced mass or effective mass to get it right. Okay, so we will look into examples later on, where we will see with or without considering a reduced mass what will happen to the results. That we will come later. Okay, so right now let us move on and continue our discussion on central orbit. Now, when we were discussing central orbit in the last class, okay, so far we have proved 3 laws of Kepler, and now we have produced, I mean, we are in a play, we have developed the platform from where we can jump forward. So, we can essentially take up little advanced dynamic problem, but before that we need to find we need to dig deep into the fundamentals once again and try to figure out some of the fundamental properties of central orbit, especially under inverse square force field. Now, in inverse square force field, we have seen which is given as f r is equal to minus k by r square, v of r, the potential corresponding potential function is minus k by r. So that f is equal to minus del v del r. This equation is valid, and we can very well write the same in terms of u, so that f of u equal to minus k u square, v of u equal to minus k u. And we have already seen that the orbit is given by L by r equal to 1 plus epsilon cos theta minus theta 0, or what we can do is we can simply consider theta 0 to be equal to 0, and we can simply write cos theta. That is also okay, assuming that our axis is at theta equal to theta 0, and this can also be written as u equal to 1 by L 1 plus epsilon cos theta. Now, L is equal to what? L is equal to L square by mk, where L is the angular momentum, k is the force constant which is here, and epsilon is equal to, so far what we have derived is a L square by mk. Now, there we have an undetermined term a. Now, it is time that we get rid of this undetermined term and we get an expression of epsilon which is which is in terms of the known variables. Now, there is another thing which is known to us in principle, which is known to us is the total energy E, which is kinetic energy plus potential energy. Okay. Although it is not known a priori, but we know that this is a conserved quantity. So, what we are going to do now, we are going to find an expression of A in terms of E and M and K and L, which are fundamental parameters of a central orbit. Now, what we are going to do is, in order to do that, what we are going to do is, we are going to use the equation du d theta square plus u square is equal to 2m by L square E minus V, right. Now, if this is the equation, we see du d theta will be given by minus epsilon by L sin theta, right. So, if we put it here, then we immediately get the left hand side as epsilon square by L square sin square theta, and then we have u square which will be given as 1 by L square 1 plus epsilon square cos square theta plus 2 epsilon cos theta. Okay. On the right hand side, please remember V can be replaced by minus k u. So, we can again we are doing everything for inverse square force field. Okay. So, we can write k times u, which can be written as 2m by L square E plus k times u will be this, we use this expression for u. So, it is k by L 1 plus epsilon cos theta. Now, we open the brackets here. So, we have 2e by L square plus, and L, please remember L is L square, capital L square by mk. So, we substitute it here, it will be L square and it will be k square m. Okay. Right. Now, if we open the bracket, the first term will be 2 m e by L square. In second term, we will have 2 m square k square by L to the power 4 into 1 plus epsilon cos theta, right. Now, here also we have to substitute the L square. L square here will be replaced by L to the power 4 m square k square, m square k square. Here also we substitute it by k square by L to the power 4. Now, look at the second term. So, there will be one term here, this plus the same term 2 m square k square by L to the power 4 epsilon cos theta. Okay. You see this cos theta term m square L 2 m square L square L to the power 4 by epsilon into epsilon cos theta, it will cancel from both sides. Okay. So, if we cancel that, what we are left with is this, and of course, we have this epsilon cos theta and epsilon square cos square theta plus epsilon square sin square theta with the same prefactor m square k square by L to the power 4. So, this will simply give us epsilon square. Okay. Okay. So, the left hand side will be m square k square by L to the power 4. Here we will have epsilon square plus, now if we put the value of epsilon, it will be s square L to the power 4 by m square k square, right. So, there will be one additional term which will be, okay, square k square, yeah. So, there was one there, so it will be m square k square by L to the power 4. Here what happens is all this cancels out, leaving only s square in the left hand side. So, we can rearrange this, and you see this term is m square k square L to the power 4, we have 2 here. So, we can rearrange this to make this s square equal to this, right. Now, we can take m k by m square k square by L to the power 4 common. So, this term will be 1 plus, so this will be 1 and this will be okay, this will be L square by m k square plus m k square, I think E here, right. Yeah, there will be a 2 term coming in, right. So, simplifying, we can write A equal to m k by L square into 1 plus 2 L square E by m k square to the power half, right. Right. So, this is the expression, final expression. Right. So, I think I made a slight mistake somewhere in the calculation. So, this is a bit complicated calculation. So, we will get an expression for A, and finally, if we substitute this expression for A in this for epsilon, then we will get epsilon equal to this. So, I request you kindly go through it once more. It is also figured out in many of the books. So, this will be the final expression for epsilon. m k, I will just check it once again. No, sorry, not this. It will be simply this. So, this will, I think it will cancel out with this one. So, leaving behind epsilon. So, the final expression for epsilon will be epsilon equal to, right. I think it was right actually. The expression for A was right, because if we multiply it with L square by m k, yeah, right. The expression for A was right. So, if we simply multiply with L square by m k, the prefactor will cancel out, and then we have epsilon equal to 1 plus 2 L square E by m k square to the power half. Now, this is a very useful expression for the eccentricity. So, the eccentricity is given in terms of mass, the force constant, the total angular momentum and total energy. And this is a very useful expression for epsilon, as we will see later, and we will keep on using this expression for solving many important problems related to the orbits in central forces. That will come slowly and slowly. So, now we have to stop this, and next class we are taking up the general equivalent one dimensional motion. Thank you.